Welcome to the Deep Dive, where we take your source material and, well, extract the most important nuggets of knowledge and insight.
That's the goal.
Today, our mission is really to cut through the noise, get you genuinely well-informed on a topic right at the cutting edge of AI research.
A really fascinating one, too.
Absolutely. We're diving into a pretty significant new paper from Google DeepMind. It's titled, General Agents Need World Models.
Catchy title.
It is. And it tackles this fundamental question that's been debated in AI for, well, decades, really.
The big one. Model-based versus model-free.
Exactly. Are these internal world models truly necessary for intelligent agents, for them to operate effectively? Or can they somehow achieve complex tasks without explicitly learning how their environment works?
Yeah, can they just sort of wing it based on experience?
Right. So this deep dive is built specifically for you, the curious learner. We've got this detailed academic paper, some really intriguing findings.
And a compelling argument, I think.
Definitely. It might just change how you think about how intelligent systems, well, how they actually learn.
And what's truly fascinating here, I think, is how this research provides a formal answer. It's not just intuition anymore.
You mean like a mathematical proof?
Pretty much. A theoretical guarantee about the internal workings of capable AI agents, that's quite groundbreaking, actually. The age-old debate. Model-free versus model-based AI.
Okay, so to really get the significance here, we need to understand that big picture, that divide you mentioned. For years, AI research has been, well, kind of split.
Down the middle.
Do intelligent systems need an explicit internal model of the world to succeed? Or can they just figure things out through, trial and error?
That's right. And we've seen impressive performance from both sides, haven't we?
We have.
Model-based agents, for instance, they often excel because having that internal map or simulator.
Their world model.
Yeah, their world model. It allows for things like formal planning, predicting what the agent might do next, which is crucial for safety.
Right, in critical domains.
Exactly. Plus, it can reduce the amount of data they need to learn and help them transfer knowledge to new tasks more easily. Lots of benefits.
But then you have the counter-argument, famously put by Rodney Brooks, right, who said, the world is its own best model.
Ah, yes, the classic line.
He suggested that model-free agents could achieve surprisingly intelligent behaviors just by reacting directly to what they perceive. Action perception loops, no complex internal stuff needed.
And to be fair, many successful model-free agents do generalize. Think about game-playing AIs. They master incredibly complex games.
Seemingly without building that explicit world map.
Right. So it really begged the question, is there a kind of model-free shortcut to general AI, maybe human-level AI, or is learning how the world works, building that model, truly unavoidable for real intelligence?
And this paper steps in and says,
It gives us a surprisingly definitive answer. 2, defining the core concepts.
okay, before we get to that answer, let's make sure we're all grounded on some key terms, because the paper builds its argument very carefully on precise definitions.
Good idea. Precision matters here.
First up, world model.
Yeah.
What exactly do they mean by that in this context?
Right. So here it's defined specifically as a predictive model of the environment's transition function.
Okay, transitions, like
Yeah.
how things change.
Exactly. Think of it as the agent's internal simulator. You give it the current state, like where it is now, and an action it's thinking about taking.
Like move left.
And the model predicts the next state, what the situation will be after the action. It's basically PST plus 1 is equals as S-A at outcode S. Exactly.
Got it. So it's not just knowing what the world is like, but predicting how it behaves.
Precisely. It's about the dynamics, the cause and effect.
Okay. And the paper talks about the environment being a controlled Markov process, a CMP. Sounds a bit technical. What does that mean for us?
Yeah, it sounds complex, but the core idea is actually quite simple. Imagine a system with distinct states like rooms in a house and actions like moving between rooms.
Okay.
A CMP just describes how taking an action in one state predictably leads to another state. The key Markov part means what happens next only depends on the current state and action, not the whole history of how you got there.
Ah, so no long-term memory needed for the environment's rules themselves.
Right. It simplifies things. They also assume it's finite, irreducible, meaning you can eventually get anywhere from anywhere else and stationary, so the rules don't suddenly change.
It's a standard mathematical framework, then. Makes the analysis possible.
Exactly. It lets them focus squarely on the world model question without getting bogged down in, say, environments that change unpredictably.
Makes sense. Okay, environment world model.
Hmm?
What about goals? the paper seems to treat goals in a quite sophisticated way.
Oh, definitely. They don't just mean get to point X. They use a formal language called linear temporal logic, or LTL, to define goals.
LTL sounds serious. What does that let them do?
It allows for a lot more richness. You can have simple goals, sure, like eventually reach status they use a diamond symbol for eventually, or do this next, or be in this state now.
Okay, basic stuff.
But crucially, it allows for sequential goals, a series of sub-goals that have to be done in order.
Like first go to A, then go to B, then activate C.
Exactly. And they talk about the depth of a goal, which is just how many steps are in that sequence. Depth 1 is simple, depth 3 is like your example.
Right.
And then there are composite goals. This is where it gets really interesting. It's basically an or condition between different sequences.
An OR. So like the agent needs to achieve sequence 1 or sequence 2.
Precisely. Their example is a robot that needs to either fix a machine, which is one sequence of actions, or go find and alert an engineer, which is another sequence. It only needs to succeed at one.
Wow, okay. That captures a lot more real-world flexibility, doesn't it?
It really does. It's not just following one fixed plan.
So environment, goals. What about the agents themselves? How do they define the intelligence they're studying?
Agents are defined by their goal-conditioned policy. Basically, it's the agent's strategy or rulebook.
What action to take given the current state and the goal it's pursuing?
Exactly. But crucially, they don't assume these agents are perfect, which is, realistic.
Right. No AI is perfect.
They define what's called a bounded goal-conditioned agent. It just means the agent might fail sometimes. It has some maximum failure rate, delta delta, for achieving goals up to a certain complexity or depth, n.
So it's generally capable but not infallible.
Precisely. A very practical, reasonable assumption for real-world agents. 3. The groundbreaking result. World models are necessary.
Okay, I think we have the pieces. Environment goals, imperfect agents. Now for the big reveal. The paper's main finding, Theorem 1, what did they prove?
Right, this is the core result.
Yeah.
Their proof shows that if an agent is capable of generalizing to these multi-step goal-directed tasks.
Meaning it's a bounded goal-conditioned agent, like we just defined, for goals with depth greater than 1, so not just immediate stuff.
Exactly. If an agent can do that reasonably well, then it must have learned an accurate predictive model of its environment, the world model.
Wow. Okay, hold on. So if an AI is smart enough to handle goals that take multiple steps, it can't not have figured out how the world works internally. Learning the capable policy is learning the world model.
That's the essence of it. They're informationally equivalent in a formal sense. You can't achieve that level of goal-directed competence without effectively learning the environment's dynamics.
Yeah, they're just helpful. It's required.
It's required. Think of it this way. The agent's policy, its rules for behavior, must somehow encode all the necessary information to predict what happens next.
So the knowledge is baked into its actions.
Exactly. And they even provide an algorithm 1 in the paper, that shows how you could, in principle, extract this world model directly from the agent's policy.
You can pull the simulator out of the behavior. That's wild.
It's pretty amazing, yeah.
And the accuracy of this extracted model, does it depend on how good the agent is?
Absolutely. The accuracy gets better as the agent gets closer to optimal, meaning its failure rate gets smaller.
Lower failure rate, better model.
Right. Or as it learns to handle more complex, longer horizon goals, higher depth in.
Tackles harder problems, needs a better map.
Exactly. And a key consequence of their mathematical bounds is quite powerful. Even if an agent has a relatively high failure rate, say it messes up fairly often, if it can still achieve long horizon goals, high N, that still implies it must have learned a highly accurate world model. Long-term planning forces deep understanding, even if execution isn't perfect.
That's a really strong claim.
Yeah.
So capability implies the model. 4, the myopic exception. When world models aren't needed. Okay, so capability implies a world model. Does this mean every agent doing anything useful needs one? Or are there exceptions?
Good question. There's an important boundary condition here. That's their Theorem 2.
What does Theorem 2 say?
It introduces the exception, myopic agents. These are agents that only care about the immediate next step, goals with depth N1.
So if an agent is just focused on, like, not bumping into the wall right now.
Yeah.
Or just maximizing the immediate reward.
Exactly. If it's only optimizing for the very next outcome, the paper proves that learning a world model is not necessary for it.
Why not?
Because its policy, its behavior, simply doesn't contain the information needed to predict further ahead. There's no procedure, they show, that could even partially figure out the environment's probabilities just by looking at how a purely myopic agent acts.
So looking ahead is the key differentiator.
Precisely. World models only become an unavoidable necessity when agents pursue goals with multiple substeps, stretching over multi-step horizons. Planning forces modeling.
That's a critical distinction.
Yeah.
It clarifies the limits, tells us when this becomes essential. It's not just any intelligence, but foresighted intelligence.
Exactly. That's the crucial boundary they draw. V, the theory and practice, experimental validation.
This is fascinating theory, really fundamental. But
Yeah.
does it hold up when you actually, train an AI? Did they test it?
They did. They didn't just leave it as pure math. They ran experiments to demonstrate their world model extraction procedure.
How did they do that?
They trained agents using standard reinforcement learning techniques in these randomly generated controlled Markov process environments, like abstract versions of mazes or simple worlds.
Okay. And then, after the agent learned a policy to achieve various goals, they used a simplified version of their theoretical algorithm 2 to recover the world model from the agent's learned behavior, just by observing how it acted.
Essentially, yes. By querying its policy for different states and goals.
And what did they find? Did the extracted model match the actual environment?
They found that the accuracy of the recovered world model consistently increased as the agent learned to generalize to longer horizon goals, just like the theory predicted.
So the better it got at complex tasks, the better the extracted map was.
Exactly. And what was really cool, and maybe surprising, is that their algorithm worked pretty well even when the agent wasn't perfectly following the strict assumptions of the main theorem.
Oh, like how?
Well, for instance, the theorem assumes a worst-case bound on failure rate, but in practice, an agent might be really bad at a few specific hard tasks, but good on average.
Right, more realistic maybe.
Yeah, and even in those cases where the worst-case failure rate was high, the average error of the extracted world model still decreased nicely as the goal depth increased. It followed the theoretical scaling pattern.
So the core idea seems robust, even if the real world is a bit messier than the pure theory.
That's what the experiments suggest, yeah. The link between capability and world models holds up in practice. 6. The profound implications. Why this matters to you.
Okay, so we have the theory, we have the practical experiments backing it up. Now let's talk implications. What does this all mean for the future of AI, for our understanding of intelligence? This feels really significant.
It is, I think. First off, it really challenges, maybe even dismantles that idea of a purely model-free shortcut to general AI.
The world is its own best model idea takes a hit.
A big one. For agents that can genuinely generalize to complex, long-horizon tasks, the kind we ultimately want, this paper says learning a world model, implicitly or explicitly, cannot be avoided.
So we can't just scale up model-free methods indefinitely and expect general intelligence to pop out without this modeling happening underneath.
That seems to be the message. It pushes the focus back towards architectures that do build models, or at least towards understanding how models emerge inside other systems, like large language models.
Which brings up emergent capabilities. We see these huge models suddenly doing things they weren't trained for. Could this paper help explain how that happens?
I think it offers a very strong hypothesis. The findings support the idea that implicit world models are the key.
How so?
Well, to get good performance, to minimize errors across all the diverse tasks they're trained on, the models are essentially forced by the optimization process to learn an implicit model of how the world works.
It's the most efficient way to generalize.
Exactly. This internal model then becomes the foundation for generalizing to new tasks, even ones they never saw in training. The paper even suggests that relatively simple training tasks, like those either-or navigation goals,
The composite goals.
are potentially sufficient to force an agent to develop quite profound world knowledge just to solve them effectively.
Wow. So simple goals could imply deep models.
It's a compelling idea, and it offers a potential pathway for explaining how really complex human abilities like causal reasoning, imagining what-if scenarios, even understanding others' minds,
Social
could
cognition.
emerge from the basic drive to achieve goals in a complex world. It all comes back to needing that predictive model.
That's a huge connection.
Right.
What about AI safety? That's on everyone's mind.
Right. This research offers something concrete there, too. It gives us a theoretical guarantee that we can, in principle, extract an accurate world model from any sufficiently capable agent, even if it's trained model-free.
Even if it's a black box.
Yes. And crucially, the fidelity of that extracted model improves as the agent gets more capable, especially on those long horizon tasks where safety issues like reward hacking often crop up.
Reward hacking.
Yeah.
Where the AI finds a loophole to get points without doing what we actually wanted.
Exactly. If we can extract the agent's own model of the world, we might be able to spot those potential misalignments or dangerous misunderstandings before they cause problems.
So it gives us a potential tool for inspection and alignment.
It provides a clear direction for future work, definitely. Developing scalable algorithms to actually do this extraction efficiently and use those models to improve safety and interpretability. It's a very promising avenue.
Does it also suggest any fundamental limits?
Yeah.
Is there a ceiling to AI capability implied here?
I think it does suggest a kind of grounding. Our own ability as humans to learn accurate models of the real world is limited, right? The world is incredibly complex, noisy, constantly changing.
True. We never have a perfect model.
Well, Theorem 1 implies that training a truly general AI agent for real-world tasks is at least as hard as learning an accurate predictive model of that world.
So the difficulty of building the agent is tied to the difficulty of understanding the world itself.
Exactly. An agent's ability to generalize, its ultimate capability, is fundamentally bounded by its ability to learn how the world actually works. You can't be smarter than your understanding allows. 7. Connecting the dots. Placing this research in context.
This is really tying a lot together.
Yep.
And you mentioned this connects to other areas of AI research. How does it fit into the bigger picture?
Yeah, it slots in quite nicely. Think of that classic AI triangle.
The one with the environment model, goal reward, and policy at the corners.
That's the one. We know if you have the model and the goal, you can do planning to find the optimal policy.
Right, standard planning algorithms.
And if you have the model and you observe an agent's optimal policy, you can often work backwards using inverse reinforcement learning or IRL.
To figure out what goal or reward function the agent must have been optimizing for,
Exactly. So what does this paper do?
it fills in the missing link.
It completes the triangle.
Yeah.
It shows that if you have the agent's policy, its behavior, and you know its goal, what it's trying to achieve, using that LTL formalism, you can determine the environment model, the transition function, how the world works. It connects all three vertices. They actually have a figure showing this in the paper.
Very neat. Okay, what about mechanistic interpretability, or MI? That field is all about peering inside models, like neural nets, to find these representations. How does this relate?
It's a really interesting comparison. Both fields are trying to show that agents learn world models, absolutely.
But they go about it differently.
Very differently. MI typically tries to dive deep into the network's activations, looking for specific neurons or circuits that correspond to states or objects, trying to map the internal machinery.
Right, finding the grandmother cell or whatever.
Kinda, yeah. This paper's approach is quite different. The extraction algorithm works purely from the agent's policy, its input-output behavior.
Doesn't need to look inside the black box.
Exactly, which makes it a weaker, potentially more universal assumption. It could apply even if we have no access to the agent's internals. It also ties the model's existence to the agent's capability, its performance bounds, rather than its specific architecture.
And you mentioned it's unsupervised.
Yes, critically. It aims to recover the true dynamics of the environment the agent is operating in, not just map out the agent's internal, possibly flawed, subjective beliefs. It's trying to get at the ground truth the agent must have learned.
That's a key difference. And finally, you touched on how this might support older theories in psychology or neuroscience.
Exactly. Think about it, so many theories about how we think, from Piaget's constructivism to modern ideas like active inference or predictive processing.
They all kind of assume we have internal models of the world, right?
They absolutely do. It's a foundational assumption in much of cognitive science. This research provides a strong theoretical justification for that assumption. It shows why goal-directed agents must acquire world models to achieve flexible, intelligent behavior.
So instead of just assuming the models exist, we can assume a certain level of competence.
A measurable ability to achieve complex goals.
And that implies the world model must exist, and this paper even gives a way to potentially find it.
Precisely. It puts those psychological theories on firmer theoretical ground, linking competence directly to internal modeling.
Outro.
Wow. Okay, this deep dive is really unpacked. Well, a profound idea, I think. That at the heart of any truly general intelligent agent, one that can actually navigate and achieve complex goals in our messy world, there has to be an internal predictive model of that world.
It's not just a nice to have or one possible
Right.
strategy,
It's necessary. The paper argues it's fundamentally required.
which means that huge challenge understanding and modeling our complex environment isn't something AI can just cleverly sidestep on the path to generality.
No shortcuts.
No shortcuts. It's fundamental. And for you, the listener, this provides, I think, a really powerful new lens, a way to view both the incredible capabilities we're seeing in AI and also its inherent limitations, which are tied to the difficulty of modeling the world itself.
So the next time you hear about an AI doing something surprising, something that seems genuinely intelligent,
Maybe pause and think. Okay, what kind of world model must it have silently built inside itself to be able to do that?
and if we could somehow extract that model, like this paper suggests is possible, what else might we learn about the AI's thinking, maybe even about our own?
It definitely sparks a lot of questions. We hope this deep dive has helped you cut through the noise, feel genuinely well-informed on this piece of research, and maybe given you some things to explore on your own.
Hope so.
Until next time, keep digging deeper.